Hey everybody, this is Larry. This is me going to do an extra question for today. I actually need to go out and get food, so I'm going to just pick a medium for today. I have a lot of medium problems anyway, so yeah. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's medium problem. That was an SQL problem, so I'm trying to obviously not do SQL problems, but I mean I need to do them so that I stop getting these things. But we'll think about it later. Okay, so today's bonus problem is actually not a premium question, so I guess eventually we'll get through them. 813, largest sum of averages. Okay, so what we're partitioning the array at most k non-empty adjacent subarrays. So we're trying to do this 3 times. This kind of reminds me of the contest problem that we had recently, but maybe. The score of a partition is the sum of the averages of each subarray. So 9, okay. This is equal to 20. We could have also partition this, for example, but then that would be 13, which is worse. Okay, so we're going to maximize the score you can achieve with all partitions. Okay. Let me think. Oh, well, n is 100 is a really awkward in that I'm not gonna lie. So initially I was thinking about, maybe just because I was thinking about the other one, I was thinking about some greedy type problems. The idea is that in theory, you know, like, I mean, I don't know how to put this together, to be honest, or like, you know, I'm still in the conception or conception stage, or abstractions now, or whatever, right? Just thinking stage is what I'm trying to say, but with a bigger word. But the idea is that, okay, for example, if you have a really big number, you want that number to you want that number to stand by itself, because then it has a bigger impact at the sum. But maybe not. I don't know. But I was hoping to kind of maybe explore and feed on that idea. Maybe there still could be a thing, but given that n is 100, then we probably can do something more brute force is what we're going to do. Can we? And the first question is, can we do something with n squared? Can we do something with n cubed? Right? So the first thing to notice is that we can definitely do a suffix type thing, right? The suffix dp, meaning that the answer of a suffix, if we are able to build the optimal subproblem for the suffix, then we can kind of merge it with the existing thing, right? And then the other thing is that okay, if we do that, that's going to be n squared, but we don't take account k. So, well, the easy part is just take account k, and taking account k will make it n times k times n, so n squared times k, and this is just in my head. We'll go over it. You know, if you didn't follow along that, it's fine. We'll go over it in more detail in a sec, but that's basically my thought. I just want to illustrate my thought process into why I'm committing it to it before, you know, like, I don't want you to be like, oh, like Larry implements something and it does, you know, it's too slow, right? Or how does he know, right? But basically I just thought about it, and this is, and like I said, if that part went too fast, it's a lot of it's just due to experience. So definitely we'll actually explain the problem. Don't worry. At least it's, you know, give it a good attempt. But yeah, but the idea is that if, and you know, this would depend on knowledge of dynamic programming, right? So basically the current thing is having the suffix index or suffix of this plus or another dimension is just how many k's we have left, because we have to kind of partition them into, you know, into k different subarrays or whatever, right? So yeah, so then if index is equal to n, then what happens? If k left is equal to 0, then we return 0. Else, then that means that we still have arrays left over, so we want the score to be something like negative infinity, right? Because we don't want this to be it's not a, we didn't use up all the numbers, so we have to kind of consider that. Okay, and then okay, right? So then now because we still, like, and some of this is a little bit cheating in the sense that it is working backwards from knowing that we only have 100 elements, because then now just as a back of the envelope, indexes goes from 0 to n, k left goes from 0 to k, which is also 100, right? So this is 100, and that means that we can do a for loop from an O of n for loop, which we'll show in a second, and then that'll be 100 cubed, which is fast enough, right? Because that's just a million. Okay, so up to here, now we can go, okay, yeah, let's just say current sum is equal to using just this one number for this thing, right? And then now for I in range of index plus 1, n maybe, then, oh, and here maybe, we'll have something like best is equal to 0, maybe 0 0.0, and then best is equal to max of current sum, or best, no, that's not current sum. Well, current sum plus largest suffix index plus 1, k left minus 1, right? Because we used 1k. Actually, we should make sure that if k left is equal to 0, then we also return negative infinity, because that means that we ran out of partitions, but we still have numbers left. So we don't want that to be a possible answer, which is why we use a negative infinity to be like, okay, sir, you need to step back from your recursion stack. Okay. So yeah. Okay. So then now that's for one number. Maybe we can win that. I guess I don't know why I wrote it this way. Maybe it's fine, because we could just do also current sum is equal to 0, right? We can do something like current sum plus, and this is actually wrong. I did it wrong. My fault, friends. Largest suffix of I plus 1, and we actually want to start at the index here then. I plus 1, k left minus 1. This assumes that k left is greater than 0, because otherwise we would already returned early. Unless k starts at 0, then maybe, no, it's okay. So then we add that to the current sum, and then of course we actually want to do this thing, but this formula is wrong, because it's not the current sum, it's the current sum divided by the count, right? So maybe we add count is equal to 0, and then count we increment. What is this going on? I think this should be, what am I doing? Okay, right? So basically the current sum is just basically the prefix sum, or not the prefix sum, but just like the subarray sum of the numbers that we're doing, and then now we have to divide it for the average, right? And also it's not a division thing, so yeah. And then after we consume this number, we go to the next number in k minus 1. And then I think that's it, really. So then now we go largest suffix from 0 to k, and this should be good, except for the time limit exceeded. Yeah. It doesn't really time limit exceeded here, but it's going to time limit exceeded, because that's just how these things are, right? This is exponential, and exponentials are pretty sad. So basically, we just add our general dynamic programming technique. So we have Hash is equal to force times k plus 1 for so then now we have an n by k array, or matrix, if you will. Right, and then here now we can just go hash of index k left, C# notation by accident, is equal to true, and then yeah, cache of index k left is equal to best, and voila. I mean, of course we should still check for it. That would be nice, actually use the cache. And that's pretty much it, hopefully. Yeah, this is ran actually a little bit slower, but as you can see when you submit, everything is friendly. So yeah, as we said, we have the total time, as I always do, is just number of inputs times time per input. So number of inputs is going to be n times k, or all of it. We can make it if we try. Okay, and then each input does O of n work here, possibly. So in total, it's going to be O of n squared times k. and space is the same logic, except for each input only takes O of one space. So this is going to be O of n times k. Cool. Can I always submit it? Okay, I think so, right? Yeah. That's pretty much it. Let me know what you think. Can you see all of it? You can see all of it before I type all this stuff, so maybe go back a little bit. Let me make this slightly smaller so you can see all of it in one page for a second. Okay, close enough, I think. That's all I have with this one. Let me know what you think. Stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye-bye.